This might be a bit of an unpopular opinion, but I didn't really care for Oppenheimer. I thought the film went too far into the troubled genius trope, neglecting Oppenheimer's very real mental health issues that he struggled with. I also thought the film could have explored Kitty Oppenheimer's alcoholism a bit more than it did. Minor critiques aside, Oppenheimer left out a very important part of the Manhattan Project that, without its existence, the Trinity test probably never would have happened, and Oppenheimer would never say those words he's now famous for. You know the ones. Now I am become death, destroyer of worlds. Hello and welcome to the Chemist's Codex. My name is Peter. I like to talk about chemistry and movies and TV shows and D&D and whatever else might catch my interest. So if any of that sounds interesting, make sure you subscribe so you don't miss my next video. About an hour into the film, there's a scene where Oppenheimer and his gathering of scientists are discussing the mechanism needed for the atomic bomb, and they bring up how much uranium and plutonium they're going to actually need. And uranium is fairly easy to get. You can just mine it from the ground and then you need to enrich it. But plutonium is a bit trickier since it's not naturally occurring. So, where did the Manhattan Project get their plutonium? The answer is mentioned in the film only once, and not even in relation to plutonium. When Oppenheimer is describing the network of sites and labs needed for the project to General Groves, he mentions Hanford. And the Hanford site is where most of the plutonium needed for the Manhattan Project was produced. Although one little detail that I kind of find interesting is all those sites have since become national labs. Los Alamos became Los Alamos National Lab. Lawrence's Rad Lab at Berkeley became Lawrence Livermore National Lab. The site in Oak Ridge, Tennessee became Oak Ridge National Lab. And the site in Chicago became Argonne National Lab, with, of course, the Hanford site leading to Pacific Northwest National Lab. Anyway, the Hanford site played a very important role in the Manhattan Project, as did Glenn Seaborg, a very noteworthy scientist the film also neglected to mention. And the Hanford site is still important to this day. It is the site of the largest environmental cleanup in United States history. So how exactly do we make plutonium? Some of you might be aware that uranium is the heaviest naturally occurring element. That's right, uranium is natural. But there are elements beyond uranium, so where did those come from? Well, it depends on the actual element. But before I get into how we make new elements, I should probably go over some basics about nuclear reactions and isotopes. And I understand not everyone is going to care about this, so if you want to skip over this section, you can just go to the next chapter or this time code. Isotopes are relatively simple. Every atom is made of protons, neutrons, and electrons. The protons and neutrons form a central mass called the nucleus, and the electrons are sort of zipping about around the nucleus in their orbitals. The number of protons will determine the element that it actually is. This is called the atomic number. Hydrogen will always have one proton, and uranium will always have 92 protons. The number of electrons will determine the oxidation state and charge for the atom or ion. When you have a number of electrons equal to the number of protons, the atom is considered neutral. Now, the number of neutrons will determine an element's isotope. Isotopes are just atoms of an element with differing numbers of neutrons. And we refer to isotopes by the total mass number of the atom. So, for example, there are three common isotopes of carbon. You have carbon-12, carbon-13, and carbon-14. All of them will have 6 protons, but there will be differing numbers of neutrons. Now, there are three main types of nuclear reactions. There's alpha decay, beta decay, and gamma decay. Alpha decay is just when an atom ejects an alpha particle, and an alpha particle is just a helium-4 nucleus. 2 protons, 2 neutrons. This type of decay will lower an atom's atomic number by 2. Gamma decay is relatively simple. When you have a nucleus that's in an excited state, it has some extra energy to it. It can emit a gamma photon and release that energy. That's really all gamma decay is, just a release of a gamma photon. Now, I skipped over beta decay because it's a bit more complicated than the other two. There's really two types of beta decay. There's beta minus decay and beta plus decay, or positron emission. Beta minus decay is typically what we're referring to when we talk about beta decay. It's the process through which a neutron becomes a proton through the emission of a beta particle. And a beta particle is really just an electron. Positron emission is very similar. It's the process through which a proton becomes a neutron through the emission of a positron. And a positron is just an electron with a positive charge. It's the antimatter equivalent to an electron. These base reactions are ultimately what allow us to make new elements. We start with a target material, some amount of a starting element, and we bombard it with some sort of particle, typically the nucleus of another element. And when these two atoms collide, they can fuse together to create a heavier element. This heavier product can then undergo the various types of radioactive decay, and in the case of beta decay, it can lead to the discovery of new elements, especially if what you produced is right below that desired element. Now, earlier I mentioned Glenn Seaborg, a key scientist of the Manhattan Project that Oppenheimer didn't even mention. I mean, they put in Feynman's bongos, but they couldn't find the time to mention Seaborg even once. Can you tell I'm salty about this? Anyway, Glenn Seaborg was a chemist who primarily grew up in Los Angeles. I'm not going to go too much into Seaborg right now because I think he's deserving of a video all of his own, but I just want to go over some of his scientific achievements to show how baffling it is to me that Oppenheimer didn't even mention him. Firstly, Seaborg was a major contributor in the field of nuclear medicine. He discovered several isotopes that were used in the diagnosis and treatment of diseases. He also developed the concept of actinides, which led to the periodic table being redrawn to how it is today. Secondly, Seaborg helped discover 10 new elements, including plutonium and element 106, which would later be called Seaborgium, named for him while he was still alive. Imagine the honor it would be to have an element you helped discover named after yourself while you are still living. Thirdly, directly relating to the Manhattan Project, Seaborg developed the process that was used to isolate plutonium. It was this process that they used to secure the plutonium needed for the Trinity test and the Fat Man atomic bomb. Seaborg also advised 10 different presidents during his life. He was a major advocate for the commercialization of nuclear energy, and he contributed to the restriction and non-proliferation of nuclear weapons. He also was a major advocate for science education and wanted to award funding just for the sake of research. Seaborg is such an important figure in scientific history and the United States. It's a shame that Oppenheimer couldn't even find the time to mention his name. Now, on to what this video is actually supposed to be about, the Hanford Site, although talking about Seaborg wasn't entirely unrelated. I mentioned he developed a process for isolating plutonium. Well, the Hanford Site is where most of that plutonium was produced. Before Hanford, plutonium was meant to be produced at Oak Ridge in Tennessee, although there were many reservations about this location, largely due to its proximity to Knoxville. A major accident could lead to death, and even a minor accident could impact production, so a new site had to be chosen. Hanford was a town along the Columbia River before it was a government facility. Of course, before that, it was native land, but the United States had some destiny to manifest, so settlers moved in and established a town to help support some of the farms and ranches in the area. Of course, when the Manhattan Project needed a new place to produce plutonium and Hanford was chosen as an ideal site, the government gave the residents of the town 30 days to vacate and abandon their homes, although apparently they were offered some money in compensation, but there was a fair amount of disputes over the actual amount. Hanford was chosen as a site due to its access to large amounts of fresh water and the amount of land it needed for the various facilities. It also wasn't within 20 miles of any major towns. Construction of the facilities began in 1943 and finished after about a year. This construction included building 3 nuclear reactors and 3 processing plants. The most notable of these reactors was the B reactor, the world's first plutonium-producing reactor. The B reactor produced the plutonium that was used in the Trinity test for the Manhattan Project and the bomb that was dropped on Nagasaki, Japan. Many of the employees working at Hanford had very little idea of what it was they were actually working on, only that it was to help the United States win the war. After the relative success of the Manhattan Project, there was a brief lull in productivity before it ramped up to meet the government's demands during the Cold War. During the 1960s, many of the older reactors were shut down, leaving only the most recently built one, dubbed the N reactor. The N reactor was the only dual-purpose reactor in the United States, producing plutonium for weapons and steam for electricity. The N reactor continued to produce plutonium up through the late 80s. In 1989, the Department of Energy, the EPA, and the Washington State Department of Ecology entered into an agreement to clean up Hanford. For nearly the entire time Hanford was active as a plutonium production site, there were protests over the probable environmental impacts. In the 1980s, the Washington State Department of Health collaborated with citizens organizations to publicize this information about contamination that originated at Hanford. These reports revealed that those downwind or upriver of Hanford received an elevated dose of radiation, and this naturally led to mass tort lawsuits since the US government knew of this and kept it secret. Over the course of these lawsuits, the Department of Energy paid about $7 million in damages. Ever since the early 90s, work has been underway to clean up the Hanford site. It is the largest environmental cleanup in US history, although it's relatively difficult due to the complex chemistry that's at play within the waste produced from the reactors. Throughout its time producing plutonium for nuclear weapons, billions of gallons of waste was produced at Hanford. Most of this waste was just dumped into holes in the ground, but about 56 million gallons was highly radioactive and contained semi-solid material and was stored in underground storage tanks. Now, since the Manhattan Project was, let's be honest, kind of rushed, the way waste was treated at Hanford was not that great. Compound that with the fact that nuclear chemistry was still a relatively new field at the time, and it's no wonder why cleaning up Hanford is such a pain. To start, the underground tanks they were using weren't really meant for long-term storage. These were single-shelled tanks comprised of a carbon steel liner surrounded by steel-reinforced concrete. In the 1950s, it was found that several of these tanks were leaking waste into the groundwater. To help combat this, double-shelled tanks were constructed, comprised of a carbon steel liner surrounded by an additional steel liner to help prevent leaks. These were separated by about 2.5 feet and came equipped with a leak detection system. A good chunk of the liquid waste from the single-shelled tanks was moved into the double-shelled tanks. Of course, that didn't stop the single-shelled tanks from still leaking. This is why part of the cleanup agreement is that 99% of all liquid waste has to be removed. And as it currently stands, I believe this has been achieved. But that does beg the question, where did all that waste go? Well, the waste goes through a vitrification process to convert it into a stable glass-like form. While still liquid, it is then poured into a steel canister where it cools and solidifies. The most radioactive of this waste is meant to be stored in some sort of national repository. Where exactly that repository is a topic for another time. But even with all that liquid waste removed, the tanks aren't exactly empty. There's still a bunch of precipitate that has crystallized out from that liquid, as well as a bunch of semi-solid waste that has taken the form of a sludge. And yes, sludge is the term that is commonly used for this waste. The sludge and salt cake is also vitrified like the liquid waste, but there are a few more complications. First, it's a lot more difficult to remove this waste from the tanks in a manner that is safe. And secondly, we don't really know what all of this waste is, so it needs to be characterized first before it can actually be vitrified. There is also the matter of all that contaminated groundwater. Like I said, much of the waste was just poured into holes in the ground, and it has naturally since evaporated. But this contaminated soil has been thought to create areas of contaminants within the groundwater, and these areas are moving towards the Columbia River at varying speeds. To prevent the contamination from reaching the river, the contaminated groundwater is pumped out of the ground to a treatment facility. It is then treated with various chemicals that render the contaminants harmless, and then the water is pumped back into the ground. Then, of course, there are all the facilities that need to be dealt with. Many of these buildings are also contaminated and need to be cleaned or decontaminated before they can be demolished. As an example, many of the reactor buildings are still highly radioactive, as you would expect. To deal with this, they are cocooned, where they are encased in some sort of shell to contain the radiation until it is safe to demolish them. Ultimately, the efforts to clean up the Hanford site have made significant progress over the past few decades, and I think the work that has been done to safely and effectively clean up Hanford is quite remarkable. Even still, there's a lot of work to be done. Now, I know all of this sounds pretty horrible, and it kind of is. I think the use of Hanford in the production of plutonium was reckless and unsafe. But even so, I don't want to give anyone the wrong idea about nuclear power. Nuclear energy is not as dangerous as many might make it out to be. And I don't think Hanford should be a reflection of nuclear power. If anything, I would argue that Hanford is a case against nuclear weapons. And I think the primary reason why Hanford is as bad as it is due to the demands of the United States government. And before anyone tries to cite 3 Mile Island or Chernobyl or Fukushima, those were all incidents where people were doing things they should not have been doing in the first place. And maybe someday in the future I'll make a video as to why. My point here is that nuclear energy is incredibly safe, and I believe that it is going to be needed if we are ever to phase out fossil fuels. I don't want anyone to get the wrong idea that the contamination at Hanford means we shouldn't pursue nuclear energy. Moving back to Hanford, I hope now that you can see why I'm kind of upset that it wasn't really featured in Oppenheimer. It was a major part of the Manhattan Project and is what I think a really important part of American history. While researching for this video, I was very pleased to find that Hanford actually has its own government website, detailing its history and the ongoing cleanup efforts. I've linked some of the specific sources I used down in the description, but if you want to learn more about the site and what's going on there, then I would recommend checking out hanford.gov for a plentiful source of information. And with that, I'm going to end the video here. If you made it this far, thank you so much for watching. I appreciate your time and attention. If you're not already, go ahead and subscribe so you don't miss my next upload, and I will see you all in the next video.